Welcome to this particular module. In the last module what we have done, we have seen fabrication of piezoresistive microcantilever and then use of piezoresistive microcantilever, followed by a sensor or a biosensor fabricated on a glass substrate with interdigitated electrodes and SU8 well, right. So, the interdigitated electrodes were inside the SU8 well. Use of the piezoresistor was to understand the mechanical properties of tissue, or you can say elasticity, or you can say stiffness, while the use of the biosensor with interdigitated electrodes was to understand the electrical properties of the tissue. Now, when I say tissue, you can also study the change in the electrical properties, that is the impedance of the cells. We also kind of glanced at why we have to use impedance and not resistance, right. I told you that the to hold the tissue properties intact, as soon as we place the tissue we have to have some saline solution or a media, and that will cause a parasitic effect on the overall readings, and thus there will be a double layer capacitance and many more such kind of things that will come into picture, and that is why instead of measuring resistance it is advisable to measure impedance of the material. So, we were able to understand that we can delineate or we can differentiate between the normal and the cancer tissue, is not it. Same way we can differentiate between normal cell and a cancerous cell. If you see if you have cantilever, and if this is a cell, right, and if this is a cantilever, or let us say my hand, this portion is cantilever, this is a tip, and if I press this cell I will be able to see the stiffness of the cell depending on how my cantilever beam will bend. This bending depends on the stiffness of the cell, is not it. So, this is an example. Okay. Same way, if I load this cell on or group of cells or few thousand cells on the interdigitated electrodes, like I said, these are all digits, this is digits, interdigit, right. So, if this is metal, then if I place metal next to each other, but they are not touching each other, impedance would be infinite, resistance would be infinite. Now, if I place anything on this metal, what will happen? Depending on the impedance or resistance of the material, we will be able to measure it, because now this metal will start, it is shorted with the resistance or impedance of the material, is not it. So, the point that I am making is that you can go for cells, you can understand the properties of cells, you can understand properties of tissue. We are talking about breast cancer, but that does not mean that this is only related to breast cancer. You can go for oral cancer, because when you are discussing or when you are developing sensors for non-communicable diseases like cancer, then you can take care of lot of interesting properties, right from oral cancer to breast cancer to cervical cancer to prostate cancer, and then we can also look at stomach and liver cancers. So, in principle any tissue related cancer we can understand how its property is changing from onset to the progression, right. So, that is the idea of teaching you the sensors for understanding the tissue property. Now, if I can do mechanical or if I can measure the mechanical properties, and if I can also measure the electrical properties, how about I measure both simultaneously. So, can we design a sensor that can measure the electrical and mechanical properties of the material simultaneously? Okay. With that concept, today we will see a MEMS based electromechanical sensor, right, fabricated using flexible substrate, all right. So, if you see the screen, and I will teach you the process flow in detail. This is the process flow for fabricating the entire sensor, right, and the sensor is fabricated on a substrate called PDMS, right, PDMS, alright. So, if you start with, there is a silicon substrate here, and then you have a PDMS coated on silicon substrate. So, PDMS spin coated on silicon substrate. If you see the third one would be the gold is deposited and is patterned in this particular region. Gold is deposited and patterned using photolithography, followed by developing a piezoresistor. Piezoresistor is made out of a material called PDOT PEDOT colon PSS. PDOT PSS is a semiconducting material is a polymer, not semiconductor material, is a polymer which is a piezoresistive polymer. So, this is a conducting polymer, that is why I was confused with semiconductor. So, PDOT PSS is a conductive polymer, and it has a piezoresistive property. So, we will after we deposit the chrome gold and pattern it, we will then deposit PDOT PSS and form the piezoresistive sensors. Now, if I want to see the piezoresistive sensors, right, you can see here these are all piezoresistive sensors, alright. This is one magnified piezoresistive sensor. So, these are all SEM images. So, if I say if the first step is silicon, then second step is PDMS spin coating, third step is chrome gold deposition and lithography to form pattern, fourth step is to deposit or spin coat PDOT PSS and pattern it to form piezoresistors. Fifth step is to grow or deposit silicon dioxide on the sensor. Sixth step is to open the contact pads and to deposit a gold pad. Seventh step is to form the SU8 pillars, and then eighth step is to coat the SU8 pillar tip with gold, and ninth step would be to strip the PDMS from the substrate. Now, lot of steps I told, and I am sure you do not remember, is not it. So, we will go one by one, alright, and I will tell you how can when we fabricate such a sensor layer by layer. So, if you see the screen, what you see is this is one sensor, or you can say array of sensors, right, and these are all strain gauges, piezoresistive sensor. Then this is gold, these are all gold pads, and then finally these are SU8 pillars which are coated with chrome gold using lift off technique. So, we will go one by one to fabricate this particular sensor. Let us see how can we start. So, I will show you the process flow in detail. First step is you take the silicon substrate, silicon. Second step is to spin coat PDMS on silicon substrate. So, let us say this is your PDMS, alright. Then third step is to deposit. So, this one is PDMS, this one is still silicon, this substrate is still silicon. Third step is to deposit chrome gold on PDMS. So, let us say we have now silicon, we have PDMS, and this one will be your chrome gold, alright. Next step would be to pattern this chrome gold, is not it. So, for patterning what we will do? Photolithography, right, we will perform photolithography, and to perform photolithography we have to first spin coat photoresist. So, this is your photoresist, Okay. And this will be my photoresist. I will say it is positive photoresist. After spin coating photoresist, what is the next step? Next step is I will go for soft bake. Soft bake. Soft bake is done at 90 degree centigrade for 1 minute on hot plate, right. After soft bake, I will load the mask to form my chrome gold pattern, right, and this mask will be bright field mask. Mask would be bright field mask. All right. So, if I take a cross section, you see this particular first one, this step, okay, silicon substrate, we can also have oxide, and then we have PDMS, then we have to pattern this. So, if I take a cross section, I will be able to only see this kind of layers, right, and that is why we have been representing the mask, which is our bright field mask, in this particular format. After that one, the next step would be to expose this photoresist with UV lithography, UV light, ultraviolet light. When I expose it, next step would be to unload the mask and perform and dip this wafer in photoresist developer. When I dip this wafer in photoresist developer, what will happen? The photoresist will get developed. Now, because it is a bright field mask and there is a positive photoresist. So, what will happen? So, what I was telling you here is that what will happen when we expose the photoresist with a bright field mask and our photoresist is positive photoresist. So, as you all know now that when we use bright field mask and when there is a positive photoresist, the area which is not exposed will get stronger. The area which is not exposed will get stronger. So, this is my positive photoresist. Correct. This is positive photoresist and you can see that the area which is not exposed, you see this bright field mask, and the area which was not exposed got stronger. Now, after this the next step would be hard bake, correct, hard bake 120 1 minute hot plate. After you perform a hard bake, the next step would be you dip this wafer in chrome gold etchant. First chrome etchant, then you wash it, then gold etchant, again wash it. So, washing is called rinsing, to rinse it, RINSE, rinse it. So, chrome gold etchant. If I dip this wafer in chrome gold etchant, what will happen? I will have a substrate which is my silicon substrate on which there is a PDMS, on which my chrome and gold will get etched from the area which was not protected by positive photoresist. This area, like you have seen here, is not protected by positive photoresist. So, the area which was not protected by photoresist, that will get etched in the chrome gold etchant, correct, easy. Next step would be I will dip this wafer in acetone. If I dip this wafer in acetone, what will happen? We will have silicon with PDMS and chrome gold pattern, is not it, chrome gold pattern. So, now this will be my chrome gold, this is PDMS, this one is silicon, right. So, if you see here, let me just rub things up. So, it becomes little bit easier for you to understand. Okay. So, what we have done? We have taken a silicon substrate, you can take an oxidized silicon substrate on which we have spin coated PDMS, right, silicon or silicon oxidized silicon. Then we have PDMS on this silicon, right. This one, which is step number 3, is your chrome gold patterned on silicon dioxide or oxidized silicon substrate, alright. So, to come to this particular step, which is step number 3, we have to perform the photolithography process. So, this is how we have done. Again I am repeating, the first step is take a silicon substrate, second step is spin coat PDMS, third step is you deposit chrome gold using physical vapor deposition, it can be e-beam evaporator, it can be thermal evaporator. So, the fourth step is that we have to spin coat a positive photoresist, which is shown here, and then perform soft bake at 90 degree centigrade 1 minute on hot plate, followed by loading a mask. This is our bright field mask, and then exposing the photoresist with UV light. Then the next step would be photoresist developer. The unexposed region would be stronger because we are using positive photoresist. After this, the next step would be to dip this wafer in chrome etchant. When you dip this wafer in there is a chrome gold. So, gold is at the top and chrome is at the bottom. So, first we dip the wafer in gold etchant. Once the gold is etched, we rinse the wafer with DI water. Then we will dip the wafer in chrome etchant. Once the chrome is etched, we will dip the wafer in the DI water, followed by the next step. After the photoresist developer, you have to perform hard bake, which is right over here, alright. So, photoresist developer, hard bake, then gold etching, then rinse, then chrome etching, then rinse, rinsing with DI water, and after that you can see this particular step. So, this will be our 5th step, and in the 6th step what you will be able to see is that chrome and gold has been etched from the area which was not protected by photoresist. After this, the next step will be to dip the wafer in acetone. Acetone will act as a photoresist stripper, and then we have the step number 7 or the step number 3, which is shown in this particular slide, alright. Next step, if you see the next step you are looking at this particular step, which is step number 4. In this step, what you are looking at? You are looking at a strain gauge, and this strain gauge we have to fabricate using a conducting polymer, like I have discussed earlier, called PDOT. Alright, you can Google it, it is called PEDOT:PSS. Alright. So, let us see how can we spin coat this material and form strain gauge. It is exactly similar to what we have been discussing on this particular platform. So, we will start from here, and to make things easier we will just show 2 contexts, alright. Just to make it easier we will just show 2 contexts. So, if you see the slide, you have this particular substrate ready with your gold gold pattern on the PDMS, is not it, silicon. This one would be PDMS, and then you have your gold pattern in this way, is not it. So, now what we will be doing is the next step is the next step we will spin coat P dot PSS onto this chrome gold or on the wafer which has PDMS. This is P dot PSS. Alright. After this, the remaining steps are exactly similar to these slides. See, I will show it to you. The next step would be to spin coat photoresist So, we have photoresist spin coat, alright, and this photoresist is again a positive photoresist. After spin coating for positive photoresist, next step is soft bake. Soft bake 90 degree 1 minute hot plate, followed by mask. You load the mask and then you form the piezoresistor. So, if my piezoresistor looks like this, right. If I take a cross section of it, right, like this, if I take a cross section, I can only be able to see if I only two pillars like this, right, two sub like this, is not it. So, if I take a cross section of this particular piezoresistor which is made out of a P dot PSS, then for that the mask that I am showing here will look like this, and this is a bright field mask, right. Photoresist is positive photoresist and my mask is bright field mask. All right. Next step would be expose with UV light. So, exposing with UV light, when I perform exposure, the next step would be photoresist developer. When you develop this wafer in photoresist developer, what will happen? You will have your photoresist protected in the area which was not exposed by UV light. So, you have here positive photoresist, this one is your P dot PSS, this we have spin coated, you here have chrome gold, then you have PDMS, then you have silicon, all right. Now, I have to remove P dot PSS. So, I will use RI to remove P dot PSS. RI stands for reactive ion etching, reactive ion etching, right, reactive ion etching. So, if I perform RI on this wafer, what will happen? I will have my wafer which will look like okay, let me redraw it. So, it becomes easier. Let me redraw it here. I will have my wafer. So, let us not consider this particular diagram. This is my PDMS, then interdigitated electrodes, and then I will have my strain gauge. All right. So, what I have? I have here positive photoresist, then I have here P dot PSS, I have chrome gold, then I have PDMS, and that is silicon. Right. Next step is, if I dip this wafer in acetone, what will I have? I will have PDMS on which there are interdigitated electrodes, on which there is P dot PSS strain gauge. Right. If I dip this wafer in acetone, this wafer, then acetone will get stripped off. I will have P dot PSS, chrome gold, and I have PDMS, and this is silicon. So, where we have reached? We have reached this particular point where you have your piezoresistor pattern, all right. So, now you have the piezoresistors which are fabricated out of P dot PSS, right. So, understand until here that now we have a P dot PSS. So, what will happen if I apply a pressure to this particular substrate, right. If I apply a pressure to this particular substrate, to this one, then because there is a piezoresistor, it will bend and that will cause change in resistance, all right. So, we will stop our module here, and in next module I will tell you how to coat an insulating material on this piezoresistor. Then I want to make it short so that you can understand just fabrication of piezoresistor, then fabrication of electrodes on this piezoresistor. Okay. So, I will catch you in next module. Till then, you take care.